Section 14.4 is the tangent problem and the derivative, so I would pause the video and write down these notes. So a tangent line is a line that within a small area only touches the graph at that one point, and it has the same slope as the graph at that point. So think about if you were swinging a rock and released it, it would be kind of the line that the rock would take. So the slope of the tangent line is the function minus the y-coordinate of that function over the x minus the x-coordinate, and then take the limit as x approaches c of that. And then you can plug that into the equation of a line with your x-coordinate and your y-coordinate at that specific point. So using that, find the equation of the tangent line of y equals x squared over 2 at 1/1/2. So to find the slope of the tangent line, here you have your setup. You have the limit as x approaches 1 of f of x minus f of 1 over x minus 1, which leads to the limit as x approaches 1 of x squared over 2 minus 1/2 over x minus 2. So this is something that you can factor and then take the limit of. So if you haven't already done so, go ahead and pause the video and do that. So the numerator factors, you can factor out a 1/2, and then in the numerator you get an x squared minus 1, which is a difference of squares. So then that x minus 1 factor cancels, and then you can plug in 1. So you end up with 1/2 times 2. So the slope of the tangent line at x equals 1 is 1. So if you haven't already done so, go ahead and write the equation of the tangent line. So it goes through this point 1/1/2. So just use that and the slope in a point slope form, so you get y minus 1/2 is equal to 1x minus 1. So you're doing the average rate of change between f of x, or between x and c. You're just throwing a limit as x approaches 1 out in front of it. Now we're going to talk about the derivative. The derivative is a fundamental part of calculus. We denote a derivative with this little prime. So this is f prime of c, which means the derivative of f at c. The way that you find the derivative at a specific x value is that same difference quotient that we just did for the slope of the tangent line. If you ever want to find a general derivative, then f prime of x, so this is the derivative at any x value, is the limit as h approaches 0 of our difference quotient that we've been doing all year. That's why we always had to get the h out of the denominator so that you could plug in 0. So if we want to find a derivative of this function at x equals 2, you have two options. You could just use this difference quotient and your answer will be the one that you want. Or you could always do a general derivative and then you'll get something with x's in it, and then you can plug in x equals 2. The benefit of that is if you ever needed to find the derivative of the same function at multiple points, you don't have to do the difference quotient multiple times. So go ahead and pause the video and use one of these two difference quotients to find the derivative of 2x squared minus 5x at x equals 2. So I did this both ways. This is the difference quotient that will find you your answer right away. It gives you the derivative at f of 2, or at x equals 2. So you plug in 2x squared minus 5x for f of x. You end up, f of 2 is negative 2, so you end up with a plus 2 on the end. So this factors, and your x minus 2 cancels. You get 2x minus 1. Take the limit as x approaches 2 of that. You end up with a positive 3. So that's your final answer right away. If you were to want to do the general derivative first, then you set up your difference quotient with the h's. You do all of that like we've been doing all year. You end up with the limit as h approaches 0 of 4x plus 2h minus 5. So in the past, that was just your final answer. Now we're taking the limit as h approaches 0, so you plug in 0. The derivative, the just general derivative f prime of x, is equal to 4x minus 5. Now if we want the derivative at 2, you just plug in a 2 for x, and you end up with the same answer, a positive 3. So both of these are correct answers. Both of these are correct ways to do it. It just depends on which way you prefer. Here are some of the uses for the limit as x approaches c of f of x minus f of c over x minus c. So we talked about 1 and 2, the slope of the tangent line and the derivative at x equals c. We've talked about this previous one, the instantaneous rate of change of f of x at c, so the slope at one point. That leads to, if s of t is your position, then s prime of t, or the derivative, is your instantaneous velocity at that time. Also, if you have v of t, then v prime of t, the derivative, is your instantaneous acceleration, or a of t. So now we have a word problem that uses instantaneous rate of change. We have a cone that's 6 feet tall and has a radius that is changing. We want to find the instantaneous rate of change of the volume, because if the radius is changing, then the volume is changing, when the radius is at 3 feet. Okay, so here's the volume of a cone, 1/3 pi r squared h. When you're doing these, you have to look at what's changing and what's not changing. The height is not changing, so we can plug that in right away. The radius is changing, so we can't plug in the radius. We have to leave that as a variable because it's not going to be the same all the time. So again, the height is not changing. It's always 6 feet, so we can plug that in right away. So I plugged in 6 for h. So v of r, the volume in terms of the radius, is 2 pi r squared. So now we want to find instantaneous rate of change. That's one of our uses of the difference quotient. So we have the instantaneous rate of change, and we want it when r is equal to 3. So we want the limit as r approaches 3 of v of r minus v of 3 over r minus 3. So go ahead and find v of r and plug everything in and solve for the instantaneous rate of change of this volume. So into the difference quotient I plugged in v of r, so this 2 pi r squared, and then into the 2 pi r squared I plugged in 3 and got 18 pi, so the volume is 18 pi when the radius is 3 over r minus 3. So then factoring the numerator, I factored out a 2 pi, you're left with r squared minus 9, which factors into r plus 3, r minus 3. So then the r minus 3's will cancel, that should always happen. And then now at this point I plugged in 3 and got 12 pi. Notice I kept the limit notation until I plugged in 3. So you end up with 12 pi feet cubed per foot. So the volume is increasing at 12 pi feet cubed every time the radius increases by 1 foot. So this is the average rate of change, or excuse me, the instantaneous rate of change of the volume when the radius is at 3 feet, which we call v prime of 3. So this has been derivatives and difference quotients and tangent lines, which is a fundamental part of calculus.